first work, simulation of energy performance potential of HVAC system and implementation of renewable energy source achieve and ZEB of an example on office building in Niš. Is here Vladan Jovanović? Is anybody here who will present this work? No? Okay, we go to another. Clean and dry absorption, dehumifilters, and achieving the low depth point for the needs of production of lithium batteries. Nikola Popović? Ne. Wastewater treatment in industry and possibilities of their use. Is anybody? No. Energy conservation through PCM integration in building envelopments. Here. Okay. Ekrem, what is your name? Okay. Please, Ekrem, floor is yours.
Okay, welcome everyone. My topic is about energy conservation through PCM integration in buildings. Let's start with the contents. Introduction, materials and method, interest and discussion, and we will be closing with conclusions, and then questions and answers. The introduction section, I will be talking about a little bit about energy consumption in buildings and emissions. As we know, energy consumption is increasing steadily, and relatedly CO2 emissions due to the energy consumption are also increasing. And in the building sector is responsible for 35% in energy demand globally, and the resulting factor is the 38% in greenhouse gas emissions. So what's a phase change material? Phase change material, actually any material that can change its phase from one phase to another. And that way we can use its latent heat to store and release a great amount of energy, actually, thermal energy. Therefore, the phase change materials is a type of very specific materials that nearly isothermally changing its phase. Therefore, that means that it can diminish the high fluctuations of the indoor temperature, and therefore resultingly decrease the energy consumption of the buildings. So it's generally used in building envelopes to reduce thermal load, as I said, by changing its phase, and in the phase change process, a great amount of thermal energy can be stored in that material. They are also used in thermal energy storage systems for storing thermal energy and then using it afterwards. The purpose of the study is to identify the effect of PCM placement in different building envelope components. These these components will be all walls simultaneously. The PCM integration is achieved in all walls, the only roof, only north wall, only south wall, only west wall, and only east wall. And we will see the effect of wall orientation of the PCM integration on the energy saving. In all the PCM placements, the optimum melting temperatures was found, and the different thicknesses were evaluated. The optimum melting temperature is very important for phase change materials, because the main reason that we are using phase change material in the wall is to have its phase changing. Therefore, we can use its latent heat occurring in the phase change. Therefore, it's crucial to find the optimum melting temperature, and the optimum melting temperature depends on many parameters, like the wall orientation and the climate of the region, and the thickness, maybe even thickness of the PCM used, and the components of the building also. And the reason we use different PCM thicknesses is that because the latent heat utilization stops at some degree when we use PCM. So it is not like insulation material. For example, when we use 25 millimeter, it can give you the same amount of thermal energy utilization as it is as it gave us in the 15 millimeter, if that was the optimum. Therefore, we have evaluated the energy savings and the energy saving due to latent heat utilization for the different thicknesses. The materials and method, we have a basic 100 square meter building as seen, and these are the building characteristics. The double pane windows with 30 millimeter air gap was chosen, and the reference walls are consisted of concrete, 60 millimeter XPS, and outer and inner plasters. And we have thermophysical properties of building envelope materials here, and these are the U values, and these U values are standard maximum limits for buildings in Turkey actually. According to Turkish standard, outer walls is at maximum should be 0.5 in Turkey. Flat roof must be 0.25, ground and windows, as we can see here, these are the maximum values limited to the U value. And the Energy Plus building energy simulation software was used to calculate energy loads, heating and cooling loads. And in the Energy Plus algorithm, generally the conduction FD algorithm was employed for the PCM utilization. And this is the fully implicit form of the finite difference algorithm of Energy Plus. An iterative Gauss-Seidel method was used to solve the discrete linear equations with under relaxation. The aniterative method is used, actually it is necessary because this is an implicit form of the energy equation, discretized equation. A variable specific heat capacity was used in the software to simulate phase change. Therefore, in the Energy Plus, the latent heat of the material of the phase change is embedded in the specific heat capacity it can simulate the phase change. And the hysteresis phenomenon seen in the phase change was captured by the variable heat capacity given above. The independent variables which the heat capacity was dependent on were defined as follows. The heat capacity is dependent on the temperature values of the old and new one, and of course the phase state of the material. Energy saving calculations. The energy saving due to PCM or PSM integration was calculated based on the difference between the reference case and PSM case energy consumptions. The PSM is the same material actually with the phase change material, but there is no phase change, therefore no latent heat exploitation effect on the energy saving. When we use phase change material, we use energy by both sensible heat, latent heat, and also thermal resistance of the material. When we use PSM has the same capacity with same thermal resistance with the PCM and same sensible heat capacity with the PCM also. Therefore, we use PCM to evaluate the latent heat exploitation of the PCM of the material. So we can see the energy saving due to latent heat utilization on the wall, which is our main goal of using PCM in the walls. Results and discussion. We have here energy saving values depending on the layer thicknesses. This is the all wall case. So PCM are integrated on all of the building walls, lateral walls. And as we can see here, the PCM 25 case outperforms other PCM thickness, PCM melting temperatures. That means that when we use all wall cases, the optimal melting temperature will be the 25 Celsius. And in this case, 398 kilowatt hour energy saving with PCM 25 at 20 Celsius millimeter is achieved. And as we can see here, PSM energy saving increases as the thickness is increased, as we can see here also, the green line. The green line, it increases steadily because when we increase the thickness, the thermal resistance in the wall increases. Therefore, the energy saving due to PSM implementation increases. But in other cases, as we can see, they are much more higher than the PSM case because latent heat is activated. Therefore, latent heat is used in those cases. And in the best case scenario, 10.7% energy saving in the best case scenario is achieved with PSM 25. And in this case, the PCM is integrated to the flat roof. In this case also, 25 Celsius is the optimum melting temperature, and 11.6% energy saving in the best case scenario is achieved here also. And as you can see from here, the energy saving stops at some degree for the pink line. That is because of the latent heat activation stops at that thickness. That's why the optimum melting temperature is very important. And when we see all walls and the roof cases, 91.7% of energy saving is due to the latent heat exploitation, and the 96.5% of energy saving is due to the latent heat exploitation for roof also. And this result shows that it is crucial to activate latent heat when we use for energy saving in the buildings. The same cases also occur here also, north wall and south wall. And this is for west wall and east wall applications of PCM. As we can see here, PCM 27 outperforms other melting temperatures at nearly all thickness values. Therefore, the orientation of the wall changes the optimum melting temperature. And as we can see here, as we can see in the case of the green line here, PCM 29, PCM integration can be even harmful if proper melting temperature is not used. That means if we use an improper melting temperature, for example 29 Celsius in the case of the green line here, it tries to keep the room temperature at 29 Celsius. Therefore, it increases our cooling loads and therefore energy loads. So it is very important to find the optimum melting temperature. The same case also occurs here, west wall and east wall. And this is the outer wall orientation, the energy saving with respect to PCM layer thickness for different melting temperatures for east facade. As we can see here, the best placement of PCM in terms of orientation will be the south wall, but they are very close to west wall also. And this is expected because this south wall, the south wall exposure to solar radiation is higher than the other walls. So it helps to change it helps PCM to change phase. And here also the energy saving due to latent heat utilization. As we can see here also, after 10 millimeters, the energy saving due to latent heat activation is nearly stops. So after that, only energy saving occurs due to thermal resistance increase. So here we have the building components comparison, south wall, roof and all walls. And we see here that the best case for PCM placement is roof, because it provides us 11.6 point energy saving. And the other one is all walls, and it provides us 10.7% energy saving with all walls. And the last one is south. And this is the energy saving. It is same, but due to latent heat activation. As we can see here, in the all walls case, the energy saving due to latent heat activation nearly stops after 12 millimeters. And we have conclusions here. Selection of optimal melting temperature for PCM placement in outer walls is crucial, as we have seen, because it can even harm the energy saving. And improper selection of PCM melting temperature harms the energy saving and even increase the energy consumption in the case of PCM29. When PCM is applied to all outer walls simultaneously, the optimal melting temperature is found as 25 Celsius, and 91.7% of this value is due to the latent heat activation. Roof application of PCM with 25 Celsius melting temperature provides 432 kilowatt-hour energy saving, of which 96.5% is due to the latent heat activation. And in the comparison of different placements of PCM, it is seen that roof provided the highest energy saving amount with 436.6 kilowatt-hour, while all walls provided 397.8 kilowatt-hours. A maximum of 11.6 point energy conservation is achieved with roof PCM integration. And that's it. Thank you very much for your attention, and I can have questions if you like. Okay, thank you.
Just one, thank you.
Yeah.
Thank you for your presentation.
Okay.
If anybody wanting to ask something or comment, please. If no, thank you again.
Okay, thank you very much.
Okay, another work is dual use project using commercial knowledge and experience for military purpose. Georgios Bamplanis. Please, Mr. Probably we have.
If you don't have it. So good evening, I'm George Bablenis. I'm a retired Admiral of the Hellenic Navy, Marine Engineer. On the next 10 minutes, I will try to explain to you how we can use the commercial knowledge and practice in the military sector and have huge savings. This is the outline of my presentation. It's about 10 minutes, as I said. So those are the definitions used by the EU for the dual-use projects. The saying dual-use project, we mean that commercial practices and techniques can be used in military sector and vice versa. And the European Defence Fund, the EDF, very well known, or those that are working with the EU, it's a fund that's supporting this kind of projects and giving very good funding to proceed in new technologies and adopting the technologies from the one to the other sector. So the history goes back when we first met the ASTRA in Greece. That was in 2014, and at that time we understood that those guys had a very good knowledge and experience, that we decided to sign an MOU, and that MOU was renewed quite many times, and it's valid until 2026 right now. The purpose of the MOU was the cooperation between the Navy and the ASTRA in the terms of research and development, innovative technologies, energy saving, green development, staff training, and many other things having to do with the air conditioning on board of Navy ships and shore facilities. The first action that we took was in 2015, when a very big conference took place in Greece, international conference, Environment in Energy and Ships. It was an action taken by ASTRA, the ASTRA Hellenic chapter, the Hellenic Navy, and the Technical Chamber of Greece. In this conference, we examine how the civilian and military sector can cooperate, and we focus on the ATP 71. This is a NATO publication, free on the internet, you can find it, and set the terms and conditions for such a kind of cooperation. Those are a few pictures from that conference that took place in the Hellenic Naval Academy, an institution that was in place in 1884. The cooperation was continued for many years. You can see in the middle the Chief of the Navy talking on the Energy Buildings Conference of Azra in Athens. That was 2021, I think, if not wrong. And afterwards, let's do that practice. In 2020, I was commanding officer of the Hellenic Navy Logistics Command when I was conveyed to upgrade some existing facilities in order to store some sensitive materials. I'm not going to be in specific detail because a lot of those things are extremely confidential. So we had the decommission facility in that condition, and we had to move to the next stage. You can see how that thing it was. What was the outline of the project? A network of tunnels and storing chambers on the surface level with a long length and following the geomorphology of the terrain. The geomorphology and the dimensions of the tunnels could not be modified, and due to the construction reasons, the creation of openings in those facilities was totally impossible. Other restriction. The initial installation was NATO approved. The existing machinery, which was in situ of the tunnels, it was very old. The recommission of the facility should follow the new standards. It was in the 60s, and we have to go to 2020. The store items were very demanding in terms of temperature and moisture. The OEM that I've tried to find told us that the machinery was obsolete and there was no possible to repair them, and many other reasons, plus the legislation that making the project extremely difficult. Putting all together, the first answer was mission impossible. But we need a solution. At that time, I said, I have no other thing to do, so why not to call the Azra? And they came. They came, and they done a site survey. They understood the problem, and they approved to make the proper studies for resolving the issue. After a period of time, very short, they came with a study that was describing the problem, was offering the perfect solution, and they overruled all the restrictions that we have due to the legislation and NATO requirement. The major problem was to remove the system from inside and move it outside in order to save money from the non-explosive requirements that we have if the machinery was inside. When they came to us, we have the MOU that give us the possibility to act with them. All the documentation that they submitted was approved by the Hellenic Navy Technical Department. It was obvious that we have huge benefits in cost and technology. They offered the supervision of the project, and they excuse me, and they cover all the requirements of the Navy. That was the situation before. This is the situation afterwards. They installed all these things without disturbing the facility. This is how the project was going through the operation. We have special requirements for the ducts due to security reasons, so they have to install special things in order to cover that sector as well. After their effort and the successful operation of the systems, the Hellenic Navy was obliged to recognize their contribution, and they honored by the Chief of the Navy with a plaque for their contribution and help to the Hellenic Navy. Of course, you can find all that in the Hellenic Navy official site. The benefit from the cooperation. Use of approved standards. Other standards are approved everywhere. Cost reduction. Security compliance. State-of-the-art installation. Compliance with country, Navy, NATO, and other regulation. What we learn from that cooperation? How to make the impossible possible. That was the title. Listen to the expert. Azra is an expert on that. Sign in advance trustful agreements with people that they know what they're doing. Use all the available tools on the table and think out of the box. Thank you very much.
Thank you. So just a moment, if any question, comments? No? If not, thank you very much for your presentation. Since Mr. Pavlovic appeared, now he will present their work, Clean and Dry Rooms, Use of Absorption Dehumidifiers in Achieving the Low Dew Point.
Yes.
Minus 40 degrees. Dobar dan.
Pitanje prezentacije na srpskom, ima razlike ili nema razlike? Mislim, mogu na engleskom, nije sporno. Šta kažete?
Pošto ima na engleskom, idemo na engleskom.
Nikola Pavlović.
Ako...
Da.
Ako da.
So good afternoon, everybody. My name is Nikola Pavlović. I'm sorry because the presentation is prepared in Serbian, but I will try to explain each slide by itself. So the topic for today is clean and dry rooms and the use of adsorption dehumidification in reaching a low dew point of minus 40. So basically, what we need to understand when speaking about clean and dry rooms is the term itself. So the term is appearing more and more in the automobile industry and in the production of lithium batteries. When speaking about the clean room, we're speaking about a sealed environment, a sealed envelope that has removed particles from the air. So basically we are controlling the amount of particles in 1 cubic meter of air, and we are controlling also the parameters of temperature, humidity, and overpressure. In relation to the dry room, we need to keep a low dew point of minus 40. These parameters combined together make a clean and a dry room. Why is this important, especially when speaking about lithium? Lithium itself is the basis for production of the electrically charged vehicles, lithium battery that is, but lithium in its pure form is highly reactive to water. So basically lithium combined with water makes lithium hydroxide and lithium hydrogen. One is highly toxic, the other one is highly flammable. In contact with air, we have lithium hydroxide, lithium nitrate, and lithium carbonate, which are combined with molecules of water, nitrogen, and carbon dioxide. Speaking about a clean and dry room environment, this is important to make these conditions in order to keep the safety for the employers and also to keep the parameters of the battery that's being produced. In terms of, just a second. So in terms of low dew point, we have comfort climation, which is usually used as cooling and then reheating in order to reach 40 to 50% relative humidity at standard temperature of 20 degrees. And this is a low dew point of around 0. When we're going down to, let's say, pharmaceutical industry, keeping the temperature at same level at 20 degrees, we need to have the relative humidity at, let's say, 10 or 20%, which is now referencing to the dew point of 0 minus 10, and going even lower to lithium battery production, we're speaking about typical set point for lithium battery production, which is minus 40 degrees Celsius. Going forward, what are the demands when making a design for a clean room? The most important two parameters is setting the dew point and also checking the amount of people, the number of people that's going to be in one clean and dry room. These two decisions will determine the total amount of air that's going to be recirculated and the cost of exploitation of one adsorption dehumidifier. Because as we know, the recommended latent moisture load on a room per one person is 100 to 125 grams regarding to ASHRAE. When we look at the amount of fresh air or air in general used in the clean and dry room, with reducing the dew point, we're drastically increasing the amount of air being used. So for 2 people and the dew point of -30, we have around 1,000 cubic meters per hour. But going to, let's say, 4 people and a dew point of -40, this increases exponentially, keeping the same number of people and decreasing the dew point. We're now reaching 26,000, and at -60 and 4 people, we're almost at 93,000. So people are the biggest load in a clean and dry room. More airflow means more equipment, which in the end means more installation and operation costs in general. So to reach dew point -50, we need to reduce the amount of vapor in the air from 500 milliliters or grams, based on the calculation for 4 people in a dry room, down to only 4.5 milliliters or grams. So this is a substantial amount, or really low amount of moisture that we need to reach. In order to decide the necessary airflow within a clean room, we are taking the return air at the desired set point, which is -40 at this point, and we're introducing fresh air. Fresh air is then mixed within the dehumidifier, filtered, pre-cooled, and then going through an adsorption wheel to remove the excess moisture. It leaves the dehumidifier at a dew point that is lower than the set point in the room because of the differential of moisture that we need to keep. So this needs to be taken into account, and as I have mentioned, the most latent load is coming from people. Also, we have the exhaust, which is coming from the local exhaust of the machines specified by the process equipment. So basically you have some vapors that you need to remove from the room, and this is the exhaust portion of the air. And in the end, we need to account for the overpressure for the clean room to convert leakages and also to keep the standard classification of a clean room. So all of this in the end, at least the exhaust and the overpressure account in for the overpressure or this fresh air. So we need to calculate these when calculating the fresh air load. As mentioned, these are some of the latent loads that we have within the clean room. The biggest one is people. The second one is infiltration over the airlocks. But we use also the pre-dried air to make a bubble airlock in order to prevent infiltration. Then we have the load from the outside air, which is generally reduced by pre-cooling to 7 or 10 degrees. Then revision openings for the equipment. Also the size of the clean and dry room. The construction, that is the permeation and the infiltration of itself. But for the clean room, we're trying to reduce this by sealing it completely. The type of production, chemical and processes itself, which may introduce some loads from their self, and also parameters of the air on the exhaust, which are heavily induced by the ducting of the channels, the ducts. A typical clean dry room setup has material airlocks, people airlocks, which prevent infiltration from the outside, from the next, let's say, part of the facility. And this facility, as you see, has a pre-cooling coil, and as mentioned, fresh air, return air, supply air, exhaust air, and also overpressure counted in. An envelope is built in such fashion that it tends to be almost a sealed room completely. When choosing the adequate rotor, we're speaking about adsorption wheels, which are the heart of the desiccant. And this standard rotor is acceptable for most applications, which reach to -40. Going below -40, we need to change the type of the rotor, going to HPX, which is a combination of silica gel and molecular sieve. So going into this rotor, we can reach the low dew points below -40. And most of you are aware of the industry standard, which is the general adsorption wheel itself. So basically, we have a part of the process air that is pre-cooled going through the rotor. The rotor is cellulose paper impregnated with silica gel. So the molecules of water are being kept on the surface of the silica gel. And on the other side, they are being supplied to the room as the air with low dew point. In order to keep this as a continuous process, we have reactivation air, which is counterflowed within the process air. So basically, this reactivation air is preheated to a temperature of 130 degrees or something like that. And it's going through 1/4 of the rotor, and it's being exhausted to the outside atmosphere as the air with excessive moisture load. To keep this a low dew point application, we need to use a purge sector, which practically means that we are also pre-cooling a section of the air. And in the direction of the process air, we're using 1/3 or 15% of the rotor, which means that we are able to pre-cool the rotor at one point, and also by preheating the purge, we're helping the reactivation air. So thus meaning that we are reducing the needed for air reactivation energy. But this has one flaw, which means that you're using a part of process airflow and thus reducing the needed airflow that you need for the overpressure, and you need to account this when making a design for the clean and dry room. A Monter's green power purge is practically the same concept. So we have the process air, which is pre-cooled, going through HPX rotor with molecular sieve and supplied as air with low dew point. The reactivation part remains the same, but what is patented, what is heavily used is the power purge, which means that adsorption and desorption are happening continuously. In one run, you're basically removing the moisture from the rotor and reducing the temperature, while on the other side, you're helping the reactivation part by increasing the temperature for the load. And this is beneficial because you're not losing any process air in any process volume of the air. In the end, comparing these two solutions, using a unit with 16,000 cubic thousand meters per hour, at, let's say, outside conditions of 32 degrees and 22 grams per kilogram, and set point of 20 degrees and 0.07 grams per kilogram, using a green power purge can amount of energy savings of 24,000 euros calculated by prices of 0.04 for gas, for cooling, and 0.03 kilowatt euro cent per gas. And this is for reactivation, because we are reducing the power needed for reactivation, but this also translates to power needed for pre-cooling. So these are the two let's say, things that you can impact by using a power purge, because you're reducing the reactivation energy needed and also reducing the post-cooling or pre-cooling needed. Total amount saved, we see, is around 6,500 and 36,000 kilowatts hours per year. And that would be all from myself. Thank you for your attention. If you have any questions, I'm here.
Are there any questions or comments?
Thank you.
Thank you. So, next presentation is on the use of forecast control of heating system in existing buildings. That's Thomas Cholera, London University of Technology, Poland. Please, it's your.
Za Tomaža ima prezentaciju.
Hello, my name is Tomasz and I come here to your congress from Lublin, where I live in, where I work at the Lublin University of Technology. I am their associate professor, and in Lublin I am also a professional, so certified engineer. So I design KGH system, and also I supervise a building site. So that's why I have also practical experience in this regard. So as you know, to 2000 we have different goals which are expected from European Commission, and they expressed this in form of a Green Deal, Renovation Wave, and Repower Europe. We also know that we should somehow decrease the energy consumption of existing buildings. We should somehow make them carbon neutral by 2050. But also European Commission, and we know that there are several barriers. One of the barriers is there is a lack of technical and cost-effective concept of decarbonization of building. So we work on this, but we also should know that, and we know probably that around 40% of energy is used in building, which is mentioned in a lot of scientific paper, in a lot of presentation. But parallelly, we should recognize that from this 30% in Europe, around 63% is used for heating, and 15% is used for domestic hot water preparation. So that's why when we propose some kind of action measures to increase the energy efficiency, it is good and it is also recommended to try to decrease the energy consumption for heating naturally by keeping the thermal comfort in the rooms. So regarding new buildings, in new buildings you can make everything, but regarding existing ones, it is not so easy to make something because there are people living there. There are some kind of building manager already have some kind of experience, and such people do not like to have problems because they are sometimes selected. That's why the measures which we are proposing should be easy in implementation, so it should take not so much time to introduce in a building. So also such actions should be characterized by short payback time. And taking this into account, I recognize that there is a lack of method easy for implementation, which can reduce energy for heating regarding control of heating, because as we know, most of existing buildings are controlled by use of weather-based control, which is follow-up regulation, but take into account thermal interior of the building, thermal interior of the heating system, we can somehow react in advance and use forecast control, and in this way we can save energy. So that's why we already developed a product. Now is quite big interest on this in Poland. So it is easy for implementation and integration with existing weather-based control. Here is existing. Okay, you can see. Here's one of these boxes, existing weather-based control. Another one is our module, which somehow emulate the outdoor air temperature. So it was not so easy to implement it, because first we developed a method how to create a real building energy model of existing building, because as you know, the theoretical energy consumption is different than actual one. That's why, and parallelly we also recognize that, and we know that most influential outdoor parameters are outdoor air temperature, wind speed, and solar insolation. But somehow they interact on the building parallelly. So we developed a method how to extract this, each factor, in order to use it in advance in forecast control model. Besides, we also know that besides these outdoor parameters, also indoor parameters like users' preferences regarding indoor temperature, heat gains, influencing the heat used for heating, heat power required for heating. That's why we also take into account and develop a method how to easy without any sensor taking into account profiles of equivalent indoor temperature. So based on this, we have some kind of 2 stages in our system. So we have a building area where we have some kind of module which make our regulation possible, which is integrated with existing weather-based control. And we have also full system where calculations are performed. It is on our servers. So there is also API Meteo integrated. Based on this, we naturally this is graphical interface for users, for administration, where the settings can be changed for specific buildings, for a specific group of buildings. So comparing widely known and widely used forecast weather-based control with forecast control. In case of weather-based control, we use only outdoor air temperature, and as I said, it is follow-up regulation because we even do not use present value of outdoor air temperature. We use mean value from past 5, sometimes even 6 hours. So we control the building based on past measurements. But like I said, it is worth to use forecast. Especially we use also solar insolation, wind speed. We use user preferences, also forecast in case of user preferences. We use real building energy model, and based on this, we implemented forecast control, so control in advance. So naturally, there are a lot of research how to forecast energy consumption, but from such a forecast, it is the case that we also should somehow implement this in a control process. So it is not so easy because it is not the case that we should give to the building this amount of heat which is forecasted, but we should give lower in a specific hours, in a specific period of times, when we do not make a decrease in frame of thermal comfort. So here is some kind of example. We can see this black line, it is outdoor temperature, red line is power consumption. So we implemented this blue settings of outdoor temperature, and based on the coming solar radiation, yellow line. So based on this, we react on the building required energy needs in advance, and we decrease already the power consumption. This reduces, as you see, the supply temperature in a heating system. This causes decrease of required heat power and heat consumption. And based on the long-term experience, here you have some kind of links to our papers in this regard. You can somehow check it. These are open access papers. Based on this, you can see that the energy savings are from 8% to even 18%. And this kind of measures, you can see that the payback time is very low, around and below 1 heating season. So it is very good measures how to make energy efficiency, increase energy efficiency in existing buildings. So naturally, we should take into account in our system. It is taken into account that each building has specific energy needs. When you have 2 buildings very similar, the energy performance and energy use can be different. So that's why such a system should be should be implemented in a specific building. Also, building users are influencing quite have quite important influence on energy consumption. So that's why proposed method could be implemented in different climates also in Serbia. Thank you.
Thank you.
Do you have questions, comments? It's really very, very attractive topic and very important.
Thank you.
Thank you.
Except compliments. Thank you.
Ima prezentacija.
Prvu prezentaciju.
A da li je tu Vladan? Da li je Vladan tu, Vladan Ivanović?
Ne, ali to je recorded. Presentation is recorded.
Snimljena je prezentacija.
Dajte, otvorite.
Ne, nije snimljena.
Molim?
Nije snimljena, nije snimak, to je...
A nije?
Nije snimljena,
Pa dajte malo se onda
prezentacija kao globalna prezentacija.
Okay. So there is presentation, but not recorded. You can see all the slides and just to see the title.
Ništa, ja ću probati par rečenica da objasnim ovo. Ovo, stvarno ne znam šta je. Simulation of energy performance of power system and implementation of new energy source achieved za Vladan Ivanović. To ne znam, da pustite slajdove, da prelistamo slajdove samo. This is not my presentation, neither my work, so I don't know what to do, but we can go through some slides to see. Oh, this is not that presentation. Simulation of energy performance of potential HVAC system. Sad ćemo vidjeti nešto. Nema. No, there is not that presentation for the first work. But we have another problem, but we will try to solve this. Namely, my young colleague should present our works, but he's not here and he's not sent presentation for that. Nije. This is something about analysis of climate data for Belgrade from 1998 to 2022 for building energy performance simulation using the heating degree days method. So, because I don't have presentation, I'm one of co-author of this work, so I will explain in few words what's happened and what we made in this work. So, in last 2 years, we work a lot with energy audit of buildings. This is central government building in Serbia, in Belgrade, all these buildings in Belgrade. And we work that through our rule book for energy efficiency of building, according to that procedure. And we faced with a lot of problems with using that procedure. One of these problems was that we don't have days for cooling in that rule book. And according to our TOR for how we could make the energy audit, we should also do that. Another problem, and when we try to solve this problem, we collect data, we call our Republican Department for hydrometeorological department and ask him for to get this data. We get this data, we have a lot of problems to get this data because they collect data but not sell, they not share, only sell this data, and we calculate that data for decreased days for cooling. And when we have all data of temperature, hourly temperature for all days in last 25 years, we also calculate heating degrees days and compare heating degrees days for period of these 25 years, so between 1998 and 2022, and compare with our data when we use in that rule book. And we found first that in our rule book we use data for period between, I must read that, period between 1925 to 1968, ili na srpskom, između 1925. i 1968. godine. That's the data when we have in our book, this is book of Professor Todorović, and also in our rule book. In your husband's book. This is our main book in faculty. All students use that book for learning. Also, we found that in that period between last 50 years, also one professor for our faculty, Professor Živković, made one calculation that was the for heating degrees days, that was for the period between 1979 and 1995, ili još na srpskom, 1979 i 1995, for that period of that 25 years. And now we calculate another heating degrees days, and what is conclusion? First, that number of heating degrees days is smaller and smaller. In first period was 175, now is 152. In that meantime period was 177. Opet na srpskom, da se bolje razumemo, mi koristimo prema pravilniku broj od 175, u onom periodu između je bio 177, a sada za posljednjih 25 godina izračunato je 152. Of course, we used standard procedure how we calculate these heating degrees days. Also, that was data about how long is a period of heating. That was that data. And about heating degrees days, we used in this moment, according to rule book, 2,520, and we calculate that is 2,179. So, conclusion that we observed that we have less heating degrees days for 15.6% than it was in the beginning of last century. So our conclusion is that we should prepare new rule book, a new procedure, and put that better data than we now calculate. Also, we conclude that we need to put in that rule book, or that method for calculation, data about cooling degrees days and all procedure how we should calculate demand for cooling, because this is now, not now, this is the last 20 years standard procedure in all European countries. And that was conclusion. Thank you.
I would add something concerning this topic with weather data and global warming, which is absolutely crucial for many, many areas and fields, multi-sectoral topic. We are coming again back to Milutin Milanković. You know, Milutin Milanković is one of the, we think, 10 most famous and significant scientists in the world. And in that 10, there is Milutin Milanković concerning data, and Mikhailo Putin, and Nikola Tesla, you know. And what is really fantastic with Milutin Milanković, I have all his equations taken down in computer, and what is activities in that direction to see which could be value or globally distributed different values of the coefficient of solar radiation transfer through the atmosphere, so absorption, coefficient of absorption and refraction, because that is the difference, huge difference, starting with the industrial period in the world, in different parts of the world with different velocities and different intensities, and to see what could be and what will be get is as a result for exactly relevant temperatures and changes in the world. You know, there is also the fact that Milutin Milankovic also should be to him added help of other astrophysicists, because from the Big Bang space is in permanent expansion, and it means that all relation, distances, angles between different planets and so are active and influencing the whole process. So we are now trying with all his equation to precisely define parameters he was using and to see different values concerning all different actors. And I think that that's a very attractive topic, and we need a group. So I think, for example, here is a colleague very dear, Thomas Troleva, who is very, very, hard worker and researcher, and it would be fine to organize one group cooperative to do this work in absolutely very, very crucial, maybe for the future calculations and goals we would like to reach, to reduce global warming, maybe even eliminate, and so on. Okay. Thank you. Are some other comments or would you like to add, say? Okay.
So please.
Sorry, excuse me. I have a connected question. Which is the
Make
relation?
it louder.
Sorry.
Louder.
Louder. Microphone.
I'm coming from the Technical University of Civil Engineering of Bucharest,
Hold on.
and I was curious about the Serbian legislation regarding net zero energy buildings or nearly zero energy buildings. It is mandatory to have which are the levels of consumptions. It is mandatory to have new nearly zero.
No, we don't have any regulation about energy, nearly energy, or nearly zero energy building. According to my information, Ministry of Energy prepares some documents about that, but it's not finished. Also, we have always problem between, not problem, two ministries are responsible for energy in Serbia. One is the Ministry for Energy and Mining, and another is for infrastructure. So always one of these two ministries prepared this documentation. I believe that it's better in this case that the Ministry for Infrastructure prepared this document, because buildings is in that area. Not, this is energy objects, but not in that sense. Buildings belongs to infrastructure. So we don't have in this moment.
Okay. Thank you.